wanted to work through a problem that involves electrical potential energy, work done by the electrical force. So in this particular example, we're asked to imagine that we're watching an electron as it travels from the left to the right, as it moves from the left to the right. We're told that we observe it as it moves 3.2 centimeters. This motion is in an electrical field, and that electrical field, we're told, has a size of 375 newtons per coulomb. It is also directed towards the right. Based on that information, what we're going to figure out is the change in potential of the electron as it moves that distance, changing kinetic energy of the electron as it moves that distance, and the work that's done by the electrical force on the electron as it moves that distance. So we're going to figure out those three things: potential energy, kinetic energy, work done. Before we do that, I'm going to add a couple of things to my sketch. One thing I want to add to the sketch that's going to be useful. We know the displacement of the electron is 3.2 centimeters. We can calculate the change in electrical potential between where the electron starts and where the electron ends up. We can calculate that potential difference knowing the displacement in this electrical field. If you remember, the electrical field is the negative slope of the electrical potential. So that tells us the electrical field from the electrical potential. You can rearrange that understanding, that equation. The electrical potential difference is equal to minus the strength of the electrical field times the displacement from left to right. Now, we know the field strength, we know the displacement, 375 newtons per coulomb, and they're 0.032 meters. Delta V, the change in potential, comes out to be minus 12 volts. So as the electron moves from left to right, it's moving from a region of higher electrical potential to lower electrical potential. Its electrical potential has decreased by 12 volts in traveling from A to B, from the left to the right. That's one thing I wanted to add to the plot. The other thing I wanted to note on the plot, that the force on the electron is the force. Because the electron's negatively charged, the force is opposite the direction of the electrical field. When you have a positive charge, the force is in the direction of the electrical field. When you have a negative charge, the force is opposite the direction of the electrical field. So here's a case where the electron is traveling left to right. It's experiencing a force right to left. So it's like being braked by the electrical force due to the electrical field. It's being slowed down by the electrical force due to the electrical field. So just so we're aware, the electron is slowing down as it travels left to right. Okay, so this was some preliminary information, some useful information that I've added to the sketch, that I've annotated the sketch with. Let's calculate the quantities we're asked to calculate. The change in potential energy. The change in potential energy, electrical potential energy, is related to the change in electrical potential when the charge moves. And it's simply given by the product of the charge, Q, of the electron, and the change in electrical potential for the electron. So in this particular case, our electron has a charge, like all electrons, minus 1.6 times 10 to the minus 19 coulombs. Our potential change is 12 volts. It decreased, so it's minus 12 volts. And if we calculate the product of these two quantities, I got plus 1.9 times 10 to the minus 18 joules. So its electrical potential energy increased by this small fraction of a joule. It was 2 times 10 to the minus 18 joules. So electrical potential has gone up. What about the change in kinetic energy? Well, you can't create this electrical energy out of nothing. It's got to come from somewhere else. It's come from, by energy conservation, kinetic energy. If the electrical potential energy has gone up, the kinetic energy has correspondingly gone down. And so it's energy conservation that tells us that the changes in kinetic and potential energy are equal and opposite. So the change in kinetic energy is minus the negative change in potential energy. And so all I've got to do is fill in my change in potential energy. It was plus 1.9 times 10 to the minus 18 joules. And I've got two minuses. No, I've got one minus. I'm going to get minus 1.9 times 10 to the minus 18 joules for my change in kinetic energy. And so if I was to add up the total kinetic energy and potential energy at the beginning of the electron's path, at the end of the electron's path, the sum of them is the same. I've just got more electrical potential energy, less moving kinetic energy. Finally, the work done. The meaning of the work done by the electrical force in this case is simply that amount of energy that got transferred. The amount of energy that got transferred from the potential energy into the kinetic energy. The way that it's defined is that the change in kinetic energy is equal to the work done by the electrical force. And equivalently, it would be the negative change in potential energy, electrical potential energy, would be the work done by the electrical force. But either way, that work done is that 1.9 times 10 to the minus 18 joules. The minus sign meaning that we've decreased the kinetic energy, we've slowed down the electron, we've increased the stored electrical potential energy because of the new position of the electron. Anyway, that's an example that involves the important concepts of energy in the context of electrical charges, electrical potential energy, energy conservation, and the work done by an electrical force in transferring energy from potential to kinetic energy.